Okay, can you see me? Yes, okay. This thing is a little bit hard to adjust. Let me see if I could get a better image of myself here. There we go. Okay, wow, can't believe it works. Okay, so let me see if I could get my PowerPoint open. Do you see a presentation mode PowerPoint with a full screen? Oh, wait, you won't
No,
see it.
not yet.
Okay, I just realized it was not going to work until I do something here. Share, yes. Where is share? Okay, what do you see now? Do you see a full mode PowerPoint, full screen?
Yes, we do.
Okay, let me see if I can adjust my screen a little bit. I can't see. Usually, when I'm in the classroom, I could see the PowerPoint on two screens, but I can't see that now, and I'm not sure how to do it. But no, well, I guess we're just gonna have to do it this way. It makes it a little harder when I can't see the next slide on one screen and the current slide on one screen, but I'm not sure how to do that unless somebody knows how to do that and can tell me. Hmm.
Do you have your other screen next to you?
I have two screens. One screen I see the participants, the audience, and the other screen I see my PowerPoint. But usually I could see my next slide in addition to the participants.
On PowerPoint, go to the bottom right. There should be something that's on the presentation mode, and it will give you your preview of the next slide.
Bottom right. Let's see here.
It's like a little projector, like the white little projector screen.
Um, I don't see that here. I don't know why not. I don't see. Oh, okay. I mean, I don't want to use any more time really because oh,
Or
here. Oh, wait.
you
Maybe
can,
I do see it now. Let me try that. I see a projector. Hold on. Let's see what happens.
if you can click on presenter view on the top on the slideshow section, you can do it that way.
Um, I'm not. Let's see.
It will be one of the little tabs in the top towards the center of the
All right.
PowerPoint.
I, I see nothing on top. There's nothing. I see nothing on top here on my PowerPoint. Okay, let me just get started because it's not, I'm not sure I'm going to, let me just try one more thing here. No. Okay, let me just get started. So anyway, let's talk about urinary system today. You see my arrow moving around the screen there?
Yes, we do.
Okay.
Yep.
Okay. So here's my thing for the poll everywhere. And I hopefully you'll be able to do this without a problem. Okay, so here's the first question. I'm just looking at that image, and right away I see that it's what I would call a glomerulus. In clinical medicine, we've always said glomeruli for the structure in kidney, although maybe in a strict sense, a glomerulus refers only to that spherical tuft of capillaries in the center of a glomerulus. That spherical tuft of capillaries is surrounded by a bilayered epithelial capsule called Bowman's capsule. And together, Bowman's capsule and the glomerular tuft is the renal corpuscle. So when you read about this, you often will see the phrase renal corpuscle referring to this entire globular structure with a tuft of capillaries in the center and a bilayered epithelial capsule. But in the medicine that I practice, which was pathology, and I think clinicians, it's the same true for clinicians, we just refer to these things as glomeruli. We didn't bother using the phrase renal corpuscle. We usually just said renal glomeruli. So realize that these are rather interchangeable words in real life. So that's what I'm seeing here. I'm seeing the so-called glomerulus. Now, the glomerulus has a intricate little structure. If you look at it, it has, I see capillary loops, and I see the epithelial capsule, and I see the urinary space between the outer and inner layers of the epithelial capsule. And I see what looks like a tubule coming off of one end of the glomerulus. Uh, uh, it's not that difficult, but actually you have to study it a bit in order to make sense of it. Look, I think I have a roadmap here, okay? So the easiest way to do that is to look at the roadmap. Here it is. I see two figures, two drawings of glomeruli. On the left-hand side, you see a nice kind of three-dimensional looking appearance to a glomerulus. You have this tuft of capillaries. By tuft of capillaries, I mean an afferent arteriole comes into the glomerulus, divides into a network of capillaries. There's actually a network of anastomosing capillaries. Every time I read about it, I see different numbers of capillaries. But when I looked at the Netter book the other day, they said there were 20 to 40 capillary loops in there, 20 to 40 capillary loops. I can't verify that's true, but what I'm saying to you is that there's a lot of capillary loops in there. I think that's fair to say. It's a really tightly packed bundle of capillary loops, which are anastomosing. And on the outside, and eventually the capillary loops come together again and form an efferent arteriole, like you see here. So an afferent arteriole comes in, breaks up into a bunch of anastomosing capillary loops, and then exits as an efferent arteriole. And where this occurs is called the vascular pole of the glomerulus. This is the vascular pole of the glomerulus. Now, there's a bilayered epithelial capsule which surrounds this tuft of capillary loops. This is called Bowman's capsule. Bowman's capsule. There's an outer layer, which consists of parietal epithelium, and an inner layer consisting of visceral epithelium. So parietal epithelium, visceral epithelium, and they become continuous with each other. You see here, if you follow the parietal epithelium, it seems to make a U-turn here and cover the glomerular capillaries like that, right? So at the vascular pole, the parietal epithelium becomes continuous with the visceral epithelium at the vascular pole. Now, the parietal epithelium consists of flattened cells. In fact, because they're flattened, you might call them squamous epithelial cells. Their shape is squamous. So they're a form of squamous epithelial cell. The visceral epithelial cells have an unusual configuration. Those are, vaguely, you might call them stellate configuration, but I don't think that word even does justice to them. They kind of look like an octopus extending the tentacles around something. They're octopus-like. There they are. A little scary, but they do us good. We want them to be healthy. So here are these epithelial cells with many, many processes which seem to wrap around the outside of the curving capillary loops. These are capillary loops, and those processes seem to extend around them like that. These are often called podocytes. So another name for visceral epithelial cells is podocytes. And here you see the podocytes encompassing, surrounding the capillary loops. Now, Bowman's capsule with a urinary space or Bowman's space between the parietal layer of epithelium and the visceral epithelium becomes continuous with the proximal tubule here. This is the beginning of the proximal convoluted tubule right here of the nephron. The functional unit of the kidney is called the nephron. So here you see the Bowman's capsule becoming continuous with the epithelium of the proximal, actually in this case, the proximal convoluted tubule of the nephron. And there's a space inside that too. That's the lumen of the proximal convoluted tubule. So the lumen of the proximal convoluted tubule is continuous with the lumen of Bowman's capsule, which is Bowman's space or the urinary space that you see here. So we're seeing a vascular pole and a urinary pole or a tubular pole at this end. They're at opposite ends, more or less. The blood is filtered at the glomerulus. There are several layers to the capillary wall here, and the blood is filtered by the several layers of the capillary wall, making the primary urinary filtrate, which is not yet actually mature urine, if you want to call it that. The primary filtrate has to be processed within the tubular system to ultimately make mature urine that we think of as urine. Normally you filter a great deal of fluid through the glomeruli of the kidney. Every day you're filtering 180 liters of fluid into the urinary space of Bowman's capsule. 180 liters. That's like, I think, 60 times your blood volume every single day. I mean, you would dehydrate in a half hour. You would be totally dehydrated and dead, I think. If most of that fluid, 99% or so of the fluid and electrolytes and molecules are returned to your body. So the tubular system does that. It takes the primary urinary filtrate and concentrates it, returns the things that you want, and allows things that you don't want to be excreted to the outside world. At the vascular pole of a glomerulus, you have several other structures in addition to an afferent and efferent arteriole. You have the thick ascending limb of the loop of Henle, which is part of the tubular system of the kidney, returns to the glomerulus of its origin, its parent glomerulus. It returns to its parent glomerulus, and where it returns is between this I don't know how to say the groin or this crook between this cubbyhole between the afferent and efferent arteriole is where the thick ascending limb of the loop of Henle returns, and you see it pressing against this gap between the afferent and efferent arteriole right here, okay? And where that occurs, the cells and nuclei of the thick ascending limb of Henle become taller and thinner, and more, the cells are more densely packed. So the epithelial cells that make up the thick ascending limb become taller, thinner, and more densely packed. And that's what you're seeing here. That little cluster of cells is a plaque-like area or patch-like area. That's called the macula densa. So here's the macula densa of the thick ascending limb of the loop of Henle, where it abuts the afferent and efferent arterioles. Now, between the afferent and efferent arterioles and the macula densa of the thick ascending limb of Henle are some interstitial cells. These are actually extraglomerular mesangial cells, or extraglomerular mesangial cells. Another name for them is the Lacis cells, L-A-C-I-S, a French word for lace. If you like lace, you'll like the juxtaglomerular apparatus. If you don't like lace, if you're indifferent to it, maybe it's a less enjoyable structure for you. But Be that as it may, these are the C cells or extraglomerular mesangial cells. Now, looking at this diagram here on the left, you can see that there are also intraglomerular mesangial cells. That's one reason why we have this figure on the right. Here you see a continuity between the extraglomerular mesangial cells and the intraglomerular mesangial cells right here. So these mesangial cells are interstitial cells between some other structures, and they're support type cells. The mesangium is a support for the glomerular capillary loop, the supporting structure for the glomerular capillary loops, and it consists of cells called mesangial cells and matrix called mesangial matrix, and that's what you're seeing here on this diagram on the right. Now, inside the wall of the afferent arteriole are smooth muscle cells. Some of those smooth muscle cells have an unusual specialization. They are secretory cells. So there's some secretory cells in the wall of the afferent arteriole, and those are called juxtaglomerular cells. The juxtaglomerular cells secrete a protease. What is the name of that protease? What is the name of that protease? Let me think about this. Oh, I see a hand being raised. Anybody want to say that?
Actually, I don't know the answer to that one, but I was thinking like the thick ascending limb that goes up and create a macula I thought it was distal convoluted tubule, not thick ascending limb.
Yeah, this is where we get into confusion territory. Well, actually, another name. I'm glad you raised that. Another name for thick ascending limb is distal straight tubule. So, if someone said to me distal straight tubule, I'd be okay. No problem, no problem. The reason I said thick ascending limb, besides the fact that that's the way it's labeled here, is that I see it more commonly used in physiology texts. And physiology means function. So, I don't care either way, really, but I have a personal investment in one way or other. But yeah, it's the same thing. Same thing. Slightly different words, same thing. Kidney is a bit confusing. Partly it's confusing because it's difficult. It's a little difficult. It's a very intricate kind of system with a complex physiology, which we're not worried about too much today, actually. But some of these terminologies, they overlap, but not 100%. So, yeah. In fact, some books will call that distal convoluted tubule it's actually at the transition. That macula densa actually occurs at roughly the transition between, if you want to call it distal straight tubule and distal convoluted tubule, at that transition point. So I don't mind if people call it distal convoluted tubule. I don't mind if they call it distal straight tubule. But most of the time I see the phrase thick ascending limb in books. So that's what I usually use that as the word. Okay. I don't know if that's confusing or not. It might be confusing to you.
Got it. Thank you so much. I got
Yeah.
it. Thank you.
Anyway, there are these smooth muscle cells in the wall of the afferent arteriole. Remember, arterioles have a few layers of smooth muscle in their wall, and these are unusual because they have secretory granules in their cytoplasm, and the secretory granules contain renin. And renin is the protease which starts off the renin-angiotensin-aldosterone system. Renin-angiotensin-aldosterone system, RAAS, which is important in blood pressure regulation. It's important in blood pressure regulation. So the juxtaglomerular apparatus, including the juxtaglomerular cells and the afferent arteriole, which make renin, are important in blood pressure regulation. One of the functions of kidney is to help regulate blood pressure. Another function of kidney is to help regulate water balance and electrolyte concentrations in our extracellular fluids. Another function of kidney is to excrete waste products, things like urea, and then creatinine and uric acid, waste products. Another function of kidney is to maintain pH of our blood and body fluids. Another function of kidneys get rid of toxins and foreign chemicals. Waste products. So kidney has a number of important functions, but the beginning of those functions is the filtering of blood to make urine. And that's what the glomerulus is important for. So on the right-hand side here, you see a little bit of illustration of the granules in juxtaglomerular cells, and you see the interglomerular mesangial cells, and you see the extraglomerular mesangial cells, also known as the C cells. And here we see an illustration of the macula densa, which is again part of the thick ascending limb of the loop of Henle, also known as the distal straight tubule. That's complicated. There's a lot to say. You know, I won't be able to talk about everything in kidney in this interactive session today because there's too much. You know, too much. But we will talk about it more in lab. So realize that this is not the end of it. We'll talk about it more in lab, and you know, use your textbook, use the video lecture. Figures, illustrations like this provide a roadmap. When you look at histologic sections, very hard to figure out what you're looking at without a clear roadmap in your head. And this is the roadmap that I use, or everybody uses, really. Okay, so here's the two glomeruli. Every histologic section looks a little different, you know, because we use special stains, different magnifications, different preparations, et cetera, et cetera. So, but, you know, there are some commonalities, some classic features which we could identify if we really try hard. So on the right-hand side, I see the urinary or tubular pole because it's the urinary space here of the glomerulus is continuous with the lumen of the proximal convoluted tubule right there, and the epithelium of Bowman's capsule is continuous with the epithelium of the proximal convoluted tubule right there. So that's the tubular pole. On the left-hand side, I see a glomerulus again with all those nice features, except here I see this pole is the vascular pole. I see a thin-walled vessel, which is too big really to be a capillary. So I presume this is an arteriole. It's either an afferent arteriole or efferent arteriole in this region here. I don't know which. I'm not that concerned about it. I mean, there may be ways to figure it out, but it's not much of a concern right now. But that's the vascular pole. So we're seeing two poles of the kidney, and you know, you don't always see both poles at the same time. You may see one pole, you may see the other pole. You don't have to see both poles at the same time. It depends where you cut through the glomerulus, if you catch the two poles or not at the same time. In fact, often you may not catch any pole at all. You may just get a cut through the glomerulus, and there's no tubular pole, no vascular pole. It doesn't really matter. You know, if someone had a kidney biopsy, for example, in that biopsy there may be 50 glomeruli, and the pathologist reviewing that may look at all the glomeruli and find a few poles here and there to examine the structures and not find any poles in some of the other structures, but I'll put it all together, create a global assessment of the whole kidney just by looking at a whole population of glomeruli. So you don't have to see every feature in every glomerulus. Around the glomerulus, by the way, are a bunch of kidney tubules. You know, a nephron consists of the glomerulus and a tubule. A glomerulus and a tubule. Each kidney has about 1 million nephrons, which is the functional unit of a kidney, which means 1 million glomeruli and 1 million, which have 1 million tubules associated with them. Now, when you look at if you were to look at a diagram of a nephron, you would see the glomerulus, and then you'd see the tubular system coming off of it, which means the proximal tubule, the loop of Henle, the distal tubule, and actually those would merge together to form the collecting ducts, right? The nephron merges with the collecting ducts. So let's say 6 to 10 nephrons may merge together to form one collecting duct. So the entire kidney tubular system, therefore, consists of the nephrons, you know, like 6 or to 10 individual nephrons merging together to dump their fluid into one collecting duct. That's the entire, you know, really ultimately that's is the ultimate functional unit of the kidney. Although we usually just say the word nephron. Now, how do you understand the structure of a glomerulus? It's a complicated looking thing. It's kind of weird, and you wonder how can that come to be to look like this or look like this? Okay, so you go to a figure like this, and I think this is probably not entirely 100% accurate in terms of embryology, but it gives you an easy way to understand the structure of the renal corpuscle or glomerulus. During development, the tubule of the nephron is actually a blind-ended tube like this. The blind end becomes a little bit dilated, like you see here, and the capillary tuft, which is the glomerular tuft, invaginates into the blind end of the kidney tubule like this. You see here the glomerular tuft, this anastomosing network of capillaries invaginates into the blind end of the renal tubule like this. And when it invaginates into the blind end of the renal tubule, you get something resembling a glomerulus. There's a vascular pole, like you see there, giving rise to a capillary plexus, and there's a tubular pole at the opposite end, which is continuous with Bowman's capsule and the urinary space with Bowman's capsule. There you have it. By this process, it's similar like if you took a balloon and you took your fist like this, if I could put it in the screen, and you punched it into the balloon, you would get something similar. You'd get a bi-layered capsule around your fist. You know, if you get bored, you could find a balloon, blow it up, and put your fist into it, relieve some frustration, feel better, feel good about life, and studying all those hours, and say to yourself, wow, I've just made something that looks like a glomerulus. I understand a glomerulus. There it is. There it is. Okay. All right, so here's the question. Which of the following is located in the right upper corner of this glomerulus? Well, did enough. Or renal corpuscle, which is technically correct, right? We talked about enough, so it's the urinary pole, and we could vote on that. Okay, we got 170, 180. There's so much enthusiasm that so many people are voting. It's unbelievable. It's an inspiration to me to talk more. Okay, we got 181. Is that everybody? 181? I'll give it a moment just so we have, so I know what number we're going for. Okay. Okay. 182. I know there's always one more. No matter what you think, there's always at least one more. Okay, I think I'm going to stop here at 182. I'm going to make it a slow stop, all right, just in case something else shows up. Yeah, there we go. A slow stop. Check your answers. Make sure you're right. There we go. There we go. Okay. All right, let's do this question. Now I'm looking at this picture and it looks familiar to me. It looks like a picture in the textbook. It looks like a picture in the video. And I see glomerular structures here. I see a glomerulus actually. Not as nice and easy to identify as the prior picture, but it's not too bad, I don't think. But it's not the whole glomerulus. When you don't have the whole structure, you got to do a little more thinking to make sense of it, right? You have to you lose some of the context. I see some renal tubules out here. Here's a renal tubule. This is P for proximal tubule. Here I see, you see there's some capillary loops. By the way, when you cut a capillary loop transversely, you see a circle with blood inside. See that? That's a capillary loop, circle with blood inside, circle with blood inside, circle with blood inside, circle with blood inside. Here's a linear, longitudinal view of a capillary, perhaps. Okay, so there are capillary loops in there. Here's a Bowman's capsule. Here's the outer layer of Bowman's capsule, and then here's a urinary space. And this is a whole bunch of capillary loops there, forming a tuft, if you will. Here we have an afferent, labeled afferent arteriole. It's a bigger vessel, but thin-walled. Here's another bigger vessel, but thin-walled, an efferent arteriole. And they come together like this. They seem to form almost like a tent. And then here's a tubule, which is a little funny looking. It has, on one side, the tubule is rather narrow. On the other side, the tubule is rather high, columnar. And the nuclei in the high area are crowded, and the epithelium is taller. The nuclei are longer, and the cells are kind of squished together. They're squished together here. So this here is labeled D for, I think, distal tubule, distal straight tubule, which is the same as thick ascending limb, okay? And here is macula densa. This is macula densa right here. So that's the macula densa. Here's a vascular pole with the distal tubule or thick ascending limb. Coming back to the glomerulus, its parent glomerulus, the mother glomerulus. There it is. It's like going back to the mothership, the spaceship, you know, it's circulating in the sky, the mothership. If you're from another planet, well, that's what it's like. That's what it reminds me of. The tubule goes back to the mothership. I know that in the wall of the afferent arteriole are going to be specialized smooth muscle cells which contain secretory granules, which make renin, the protease renin, which starts off the renin-angiotensin-aldosterone system. So I presume in here are JG cells, juxtaglomerular cells that make renin, okay, because it's labeled, and I would expect them to be there anyway. Even without a label, I know they ought to be there anyway. That's the second component of the juxtaglomerular apparatus. And the third component of the juxtaglomerular apparatus are these extraglomerular mesangial cells, also known as Lassie cells. So the L here stands for Lassie cells. Right here, there's like a conical shaped space between the two arterioles on either side here, this arteriole, and at the base, the macula densa here of the thick ascending limb or distal tubule. So this conical space will contain Lassie cells, lace-like cells. Okay, so I've made out now the elements of the juxtaglomerular apparatus, which is important for blood pressure control. So which of the cells of the juxtaglomerular apparatus secrete renin? Well, we already mentioned that they are the juxtaglomerular cells. Here's in case you're having some difficulty recognizing structures here, which I imagine may very well be the case. Here's a diagram to look at. I see a hand go up. Any question?
So I don't know if I missed it or not, but what do Lassie cells do?
They are they
How
are
do they secrete?
They are support cells. They form a support framework to hold everything else together in the right position. They also help communication. They do several things. We'll talk more about mesangium tomorrow, but they help. There may be communication. The macula densa is a sensor of salt content in the fluid of the lumen and flow rate of fluid in the lumen, and it senses those things and communicates with the adjacent juxtaglomerular cells, the adjacent afferent arteriole and the adjacent juxtaglomerular cells, and part of the communication is via the intermediary Lassie cells. They are, those are altered in some way, and those may then further communicate with the afferent arteriole. I mean, they have several functions, but that's just probably oversimplistic view of them. Okay.
Are they also stem cells or no?
I don't know if they are stem cells per se. I mean, you may have. I wouldn't be shocked if there were stem cells in the region, but they are not per se stem cells. It would be an isolated cell that would function that way. But no, I don't think they ordinarily are regarded as stem cells. Okay. Here you see communication between the extraglomerular Lassie cells and the intraglomerular mesangial cells in this diagram here. See, you can't really see that in this histologic figure of a glomerulus. You only know that conceptually. That's why I always emphasize to you the importance of being familiar with the roadmap, because you cannot see everything in a histologic image. Just memorizing what's in a histologic image doesn't tell you all you need to know. It doesn't tell you all you need to know. You need to be able to apply this figure to this image. That's what you got to do. So this is a veterinary preparation, but it is possible to see, at least in some animal, the granules in the cytoplasm of these juxtaglomerular cells. I don't think this is true for humans necessarily, but it's true for this particular animal. Those are renin-containing cells, juxtaglomerular cells, presumably in an afferent arteriole. I can't tell really from this image, but I presume they're probably in an afferent arteriole. You could immunostain the kidney preparation for renin, do a renin immunostain, and here you see here you see a glomerulus, here you see a tubule with a macula densa right here, you see macula densa. The cells are dense, the nuclei are densely packed, macula densa, a plaque-like densely packed area. And adjacent to it, you see a kind of a sphere, a cylindrical structure cut on cross section, right? A cylinder cut transversely, and you see staining for renin. So those are juxtaglomerular cells inside probably an afferent arteriole. And you can even do electron microscopy. Here you see a cell containing lots of granules, right? You see those granules? That's probably a juxtaglomerular cell inside an afferent arteriole. And next door to it, you see here a tube with the cells becoming taller and more and thinner and more densely packed than the rest of the tube. This is the macula densa right there on electron microscopy. Then probably there will be some C cells between the afferent arteriole containing juxtaglomerular cells and the macula densa in the thick ascending limb of Henle here. So these cells here are probably EM extracellular mesangium right here, EM extracellular mesangium right there. So probably there's some kind of communication going between the macula densa and the juxtaglomerular cells in the tubule, and somehow it may be mediated somehow by these extracellular mesangial cells, besides some of the other functions they do. They have other functions. Juxtaglomerular apparatus is important in helping regulate blood pressure. We're not going to worry too much about that here because it's more of a physiologic thing, but remember the macula densa monitors the salt content, the sodium chloride content of the fluid in the tubular lumen. At the end of the tube of Henle, the loop of Henle, at the end of the loop of Henle where it's located, it's monitoring the salt content of the lumen at that point. And also it's monitoring the flow rate at that point. And if it senses if there's too much salt, too much flow, too little salt, too little flow, and communicating to the afferent arteriole and juxtaglomerular cells if they should be doing something in response to the level of fluid. So what cells secrete renin? Juxtaglomerular cells. Let's vote for that. Okay. Any more questions there? I see a hand up.
Yes, just that I find it really strange that renin, like for the vasoconstriction and in response to low blood pressure, renin has to go all the way to circulation, then the whole angiotensin 1 and 2 loop goes to the lung. Is there any specific reason, or is there any sense or logic into it? Well, and then
Well, I think controlled blood pressure is very complicated, but basically, it's a systemic process. I mean, to control blood pressure, you could cause systemic vasoconstriction systemically. You need to absorb more salt and more water. Well, that partly goes through the adrenal gland. The angiotensin stimulates the adrenal cortex to release aldosterone, which then influences the kidney. So that involves a systemic limb to that process, right? And activating the adrenal gland to secrete aldosterone is systemic. The heart may be affected. The heart may beat stronger. Uh, uh, there may be a number of other alterations as well. So yeah, it is a systemic process, not just, it is renal, partly renal by whether the kidney holds on to salt and water or excretes salt and water. It's partly, a lot of it is systemic vasoconstriction. Just think of that. That's quite easy to understand, I think. Systemic vasoconstriction increases blood pressure. Okay. I'm going to stop here at 184. I'm stopping here at 1. Okay, we're moving on. Okay, so here we have, let me see what time it is because it's this complicated subject, hard to talk about brief, too brief. It's too brief. It doesn't make any sense. If it's too long, it's not going to be good either. So anyway, on top we have a scanning electron micrograph. At the bottom we have a transmission electron micrograph. This is a scanning micrograph of a capillary loop in a glomerulus. And on the outside of the capillary loop is a podocyte, a visceral epithelial cell, which has a body. Here's the body of the podocyte. This is a big, thick process there, for example. That's a primary process of podocyte. Here, you see, primary process of the podocyte. And that gives rise to a number of thinner processes called secondary processes or pedicels, foot processes. The pedicels or foot processes place the foot on the outside of the capillary loop. Or see how they're embracing the outside of the capillary loop, kind of like a hand embracing a broom. But the pedicels not just don't only embrace the outside of a capillary loop, they interdigitate like this. They interdigitate like that. And they form little slit spaces or slit pores between the interdigitating pedicels. The filtrate going from the blood to the urinary space has to push its way through those thin slit spaces or slit pores. It's part, not the entire, it's part of the glomerular urinary filter. Okay. If we look at the same thing on a transmission electron microscopy, we see three major elements of the glomerular filtration barrier. Here are the pedicels we just talked about that we see on the scanning electron micrograph. You see here pedicel, 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 foot process, foot process, foot process, foot process. These, by the way, it's a very narrow space between them, but they also are joined by a thin diaphragm. See that? There's a slit diaphragm right there within this slit space here. Slit diaphragm, slit diaphragm, slit diaphragm, slit diaphragm. That all has to be intact in order to maintain the normal glomerular filtration barrier. On the other side are the flattened portions of endothelial cytoplasm. Here we have a part of an endothelial cell with endothelial cytoplasm, and those endothelial cells are fenestrated. They are fenestrated endothelial cells. They have windows or gaps. Here's a gap right here of a fenestration of an endothelial cell. So we see already the glomerular filtration barrier consists on one side of the podocyte foot processes with their diaphragms, the slit diaphragms. On the other side consists of fenestrated endothelial cells. And then there's a third part between the endothelial cell and epithelial cell, right? Between endothelium and epithelium is GBM, glomerular basement membrane, right here. This is the glomerular basement membrane right there. So those are three major parts of the glomerular filtration barrier, the glomerular filter. All those have to be intact for normal glomerular filtration to occur. If they get leaky, for example, you're going to start leaking too much protein into the urine. You may start leaking blood cells into the urine, get bloody urine, and so on. You may start losing important things like glucose and amino acids. You need an intact glomerular filter. If the glomerular lumina are blocked, the capillary lumina are blocked, you start getting low urine output, and then you have other problems, right? There's obstruction to urinary flow if the capillaries get blocked because of disease processes. So I'm just giving you a slight taste of what could go wrong with the kidney when there's glomerular disease. So what is not a component of the glomerular filtration barrier? I just mentioned three things which are components of the glomerular filtration barrier. Mesangial cells or mesangial matrix are not part of the glomerular filter. The mesangium supports the capillaries. It's like a pedestal or stalk supporting the capillary loops, but it is not part of the glomerular filter per se. Okay? It is a stalk supporting the glomerular capillary loops, but it's not part of the glomerular filtration barrier or glomerular filter per se. So let's vote for that.
Sir, the poll is locked.
It's blocked. It's locked. Nobody else can go on? Anybody?
No.
If it's locked, I'm
No.
gonna. Oh, here. Let me see if I can restart it. Let me see what happens here. Oops. Where am I?
Now we can
It's
vote.
open now.
Yeah. Okay. It's a poll everywhere glitch. That's a glitch. The sunspots, whatever. We got 180. Anybody else? Anybody else? It looks like we stopped here. Oh, okay. I am going to have to move on because time is merciless. Merciless. Stops for no one. 182. Okay, so I think we'll move forward. Yes. Make sure you vote for the right answer because, okay. We're going to go through this quickly and we'll talk more about this again during lab, so don't worry about it too much, but we want to get the points registered. But here, let me show you a diagram showing you what's in the renal medulla. You have the loop of Henle, which means there may be thick limbs of Henle like we see here, and thin limbs of Henle like we see there. You have the vasa recta, which are capillary loops. So you have a descending and ascending limbs of the vasa recta. And we have collecting ducts, the medullary portion of the collecting ducts. So if you take a transverse cross-section medulla, you see a heterogeneous collection of structures. You may see a collecting duct. You may see a thick limb of Henle. You may see a thin limb of Henle. And you may see capillary loops of the vasa recta. Those are all things you see. So when you go back to a picture like this, it looks something like this. Okay, I'll go through this fast because of time, but I will go over it again in the lab. Okay, the tallest epithelial cells are seen in the collecting duct. Here's a collecting duct with the tallest columnar cells, and they also, one distinctive feature is they have very sharp, easy to see lateral cell boundaries like that. You see the sharp, easy to see cell boundary? That's typical for a collecting duct. The capillary loops, what's typical then? They have squamous epithelial cells, endothelial cells lining them, and they contain blood. So these are capillaries containing blood. These are vasa recta. Now, what does a thin limb of Henle look like? Well, it looks kind of like a capillary with a flattened epithelial cell, a squamous epithelial cell, but there's no blood in the lumen. No blood in the lumen. So this is thin limb of Henle right there. Thin limb of Henle right there. And this, in contrast to the capillary, which has blood in the lumen. They look similar, but the capillary is blood. The thin limb of Henle does not have blood. Then finally, there's one tubule left over, which doesn't fit any of those criteria we just talked about. This here is a thick limb of Henle. This is epithelial. These are cuboidal epithelial cells. This is thick limb of Henle. This is thin limb of Henle. Thick limb of Henle, thin limb of Henle. So one collecting duct, vasa recta capillary, thin limb of Henle, thick limb of Henle. So what is true of this section here? The thin limbs of Henle and vasa recta are both lined by squamous cells for the reasons I just mentioned to you. So vote for that. It's a bit challenging, I have to say, but by using reasoning, you're able to figure that out. We'll talk more about this in the lab.
When
Will
you get
that
into the
be
thick
on
limb and
will that be on Zoom, Dr. Brown, or are we coming back in person?
I would think you're back because I don't think the weather will be bad tomorrow. I mean, I haven't checked, but as long as the weather cooperates, I think the powers have decreed there's class in the classroom.
Thank you.
Yeah, I know Zoom is kind of convenient, right? In some ways. Okay, we got 180. 180. Anybody else? Anybody else?
could
Get in on the
you,
action. It's free right now, anyway.
after
180.
that, could you
Anybody
go
else?
back
Anybody
to,
else? 181? 181? Okay, I'm going to stop because the time. Here we go. Okay, okay. Okay, looking at this, this is a collecting duct. It has tall columnar cells, pale cytoplasm, which I didn't mention last time, and these sharp interlateral borders between cells. Very typical for collecting duct cells, collecting duct cells. So what is a collecting duct good for? It helps determine the osmolarity of the final urine. You see, the most of the urine has already been absorbed back into the body via the tubular system, but the final adjustment is done in the collecting duct. That's where the final adjustment is done. Okay? So it's important for determining the final osmolarity, the final concentration of the urine. Okay? So E is the correct answer. Let's vote for that one. Okay, we got 181. One may be missing, so I wait a little bit. Okay, there we go. So I'm going to move forward. Oh, 183. Okay. I'm moving forward now. Okay. Vasa erecta arise from branching of, okay, let's just go here. A vasa erecta are the hairpin looped capillary network in the medulla. The hairpin capillary loop forming in the medulla. These are the vasa recta. So in a glomerulus, blood comes in the afferent arteriole, exits from the efferent arteriole. The glomeruli of the cortex are divided into two major categories. There are more superficially located cortical nephrons, which is in the mid and outer portions of the cortex. You have efferent arterioles coming off glomeruli. Those form a peritubular capillary network around the tubules in the cortex. This is a peritubular capillary network around the tubules of the cortex. About 90% of the nephrons are cortical or superficially located nephrons, which give rise to that peritubular capillary network. About 10 to 15% of nephrons are called juxtamedullary nephrons. Those glomeruli are close to the border between cortex and medulla, and the efferent arteriole of the juxtamedullary nephrons give rise to the vasa recta extending down into the medulla. Remember, these are juxtamedullary. They're just above the medulla. So 85 to 90% of nephrons give rise to the peritubular capillary network. About 10 to 15% give rise to the vasa recta surrounding long loop nephrons, which go deep down into the medulla. These go deep down into the medulla, okay? So the answer to this is vasa recta arise from branching of efferent arterioles associated with juxtamedullary nephrons. That is the correct answer. Okay, vote for that. Okay, we're at 181. 181. Anybody else? 182? Okay. I think that's it, although I don't know. We got a 183 before. So we're going to close it here. Okay, this is the last question. Looking at that picture, this is immunofluorescence. This is somebody, a 25-year-old woman with rapidly progressing kidney failure. They have an autoimmune disease. Autoantibodies are directed against collagen of the glomerular basement membrane. Because collagen is linear and diffusely distributed in the glomerular basement membrane, the immunofluorescence staining is linear and diffuse, forming a linear pattern of staining along the entire glomerular basement membrane. In other situations of glomerular disease, there are immune complexes, that is, antigen bound to antibodies, which circulate in the bloodstream, for example, which get deposited in the kidney. But when they get deposited in the glomerulus of the kidney, it forms a granular type pattern. So that would not be this case. This pattern of immunofluorescence reflects autoantibodies directed against a normal constituent of the glomerular basement membrane, not by circulating immune complexes which get deposited in a granular pattern. So by looking at the immunofluorescence, you could get an estimate of what type of disease process is occurring in somebody. Okay, so the answer here is that from the pattern, the morphologic pattern of immunofluorescence, you can guess that there are autoantibodies directed against the glomerular basement membrane. Now, this disease process is called Goodpasture syndrome sometimes. In Goodpasture syndrome, the autoantibodies are directed not only against the glomerular basement membrane, but also the alveolar basement membrane of the lung. So people like this get the strange combination of pulmonary hemorrhage and kidney failure at the same time. Pulmonary hemorrhage and kidney failure at the same time because the autoantibodies are directed against the basement membrane of both the kidney and the alveoli at the same time. So there's the...
Dr. Braun, sorry, the poll everywhere didn't register for me for number 6. Is it possible to go back before 7 is done?
I think it's kind of late. Just send me a message and I'll adjust it on the final.
Oh, thank you.
I realize that it always happens, that happens. So, I mean, I'll just send me an email and I'll just, a few days and I'll adjust it so that.
Thank you. I appreciate it.
Okay, we're almost there. 181. $184. Anybody else? Anybody else? 185. 185. 185. We're going to close it up here. Close it up. Yes. Okay, here we go, I think. Okay. Thank you.